We all like to think we're pretty good at communicating, but the truth is, our own words are just full of these hidden traps. A single sentence can mean two totally different things, and suddenly what you thought was an agreement is now a full-blown argument. So today, we're going to dive into the system that was literally designed to eliminate those traps entirely, formal logic. So here's the plan. We're going to start with the problem itself, the messiness of our own language. Then we'll see how logic offers this perfect blueprint for clarity. We'll look at how it builds a whole world from the simple idea of truth, and you'll see how it's powering the very device you're watching this on right now. And then for the finale, we'll uncover some surprising cracks in this supposedly perfect system. Okay, so first things first, why do we even need something like formal logic? Well, it's because our everyday language is, let's be honest, a double-edged sword. It's awesome for quick, casual chats where we all get the context, but it's just awful when we need to be perfectly, 100%, undeniably clear. I mean, just look at this sentence. It seems so simple, right? John saw the boy with a telescope. But this is a perfect example of how our language can trip us up, hiding two totally different meanings right there in plain sight. Exactly. Who's got the telescope? Is John using it to look at the boy? Or is the boy the one holding it? See, this is precisely the kind of ambiguity that formal logic is engineered to make completely impossible. And that really gets to the heart of it, what you're seeing here. Our natural language is super flexible, but it's messy. Formal logic, on the other hand, is rigid, but it's crystal clear. Its entire reason for being is to build statements that can only be understood one single way. So if natural language is kind of like sculpting with clay, it's intuitive but not always precise, then formal logic is like building with Legos. It gives you a set of standard blocks and a clear set of rules to build ideas with absolute mathematical precision. The whole system is really built on these three pillars. And honestly, the easiest way to think about it is like a board game. You've got syntax, that's the rulebook. Then there's semantics, that's the goal of the game. And finally, you have proof, that's your winning strategy. First up, we have syntax. Think of this as the pure grammar of logic. It just tells you what symbols you're allowed to use and how to put them together correctly. What's cool is a computer can check syntax, no problem. It doesn't care one bit what a sentence means, only that it's built according to the rules. Next up is semantics. Now, this is where meaning finally shows up to the party. Semantics is the bridge that connects our perfectly structured sentences to the real world. And it often does that by asking one really simple but powerful question. Is this statement true or is it false? And that brings us to the third pillar, proof. So if semantics tells us what is true, proof gives us a step-by-step, bulletproof way to show it. You start with a few things you know are true, and a proof lets you build this unbreakable chain of logic to arrive at new truths you can be absolutely certain of. Okay, so let's see how this all clicks together. Because that simple idea of connecting statements to either true or false, well, that's not just a part of the system, it's the engine that drives the entire thing. It's literally how logic creates meaning from scratch. This is the absolute core idea of what's called truth-conditional semantics, and it's a huge shift in thinking. Instead of, say, defining the word rain by describing water falling from the sky, logic says, nope, the meaning of the sentence, it is raining, is actually the exact set of conditions in the world that would make that statement undeniably true. And this leads us to something called semantic entailment. This is the bedrock, the foundation of all logical deduction. It's an incredible guarantee. It says if your starting points, your premises, are true, then your conclusion is guaranteed to be true. There's just no way for the premises to be true and the conclusion to be false. And we can see this perfectly with a simple truth table. This little table defines the meaning of the logical and, with zero ambiguity. You can see right there, the statement A and B is only true in one single case, when A is true and B is also true. In all other cases, it's false. It's a simple, mechanical way to build meaning that is just incredibly powerful. Now, all this talk about mechanical precision, it might seem a bit abstract, right? But it's exactly why formal logic is sitting right at the heart of the technology you use every single day. Every line of code, every app on your phone, it all relies on these principles to work right. When a programmer writes a piece of code, they need to be absolutely certain that the computer is going to interpret their commands exactly as they intended. Formal semantics gives them that certainty. It creates a strict rulebook that makes sure the logic of the code translates perfectly into the actions of the machine. So, computer scientists have a few different ways of looking at this. Axiomatic semantics is all about the promises the code makes, what we can formally prove it'll do without even running it. Denotational semantics is kind of like a universal translator, mapping the code into the pure language of math. And operational semantics is the most literal of all. It defines the code's meaning by listing out every single tiny step the computer's processor will take. Three different methods, but they all share one single goal: get rid of all the ambiguity. So, after all this talk about perfection and guarantees and precision, you'd be forgiven for thinking that formal logic is, well, infallible. But it turns out that even this incredible system for creating certainty has some really profound and fascinating limits. For starters, there's this subtle but really deep problem of circularity. Remember that truth table for and? Well, to explain what that little symbol means, I had to use the English word and. We sort of have to start with a shared human understanding of language just to get our supposedly perfect independent system off the ground. But oh man, the biggest bombshell of all, that dropped in 1931 from a mathematician named Kurt Gödel. See, before him, everyone pretty much assumed that any true mathematical statement could eventually be proven. Gödel proved this was wrong. His incompleteness phenomenon showed that in any logical system powerful enough for even basic arithmetic, there will always be statements that are demonstrably true, but which the system itself is incapable of ever proving. It was a revolutionary, mind-bending discovery that put a fundamental limit on what logic and math can ever hope to achieve. And that just leaves us with this huge question, doesn't it? Formal logic is one of the most powerful tools we have for finding certainty in a ridiculously complex world. But if even this pristine, perfect system can't capture all of truth, what does that say about our own, much messier attempts to understand the universe around us?